A caching-only DNS name server resolves queries on behalf of end devices and saves the results in a cache. A forwarding DNS name server forwards all queries to the caching-only name server and saves the result in a cache. To explain how to configure, test, and verify these name servers, I will use a pre-built RHCE practice lab. In this lab, I have 3 RHEL Linux systems. I will configure name servers on these 2 systems and use this reaming system for testing. I used VMware Workstation to set up this lab. It doesn't matter whether you use physical or virtual systems to set up the practice lab, the instructions and configuration steps for DNS name servers are the same. If you want to use physical systems to replicate this lab, you need 3 systems. You need 2 systems for server configurations and 1 for client configuration. You also need the internet connection. Connect systems with the network and note down the modem's IP address. Configure modem's IP address as the default gateway IP address. My modem's IP address is 192.168.29.1. Therefore, I will use this IP address as the gateway IP address on all virtual machines. Use an IP address from the gateway IP addresses network for each system. I will use the IP addresses 192.168.29.100/24, 192.168.29.101/24, and 192.168.29.102/24 for RHEL Server 1, RHEL Server 2, and RHEL Client. Configure the IP address 8.8.8.8 as the DNS server's IP address. If you know your ISP's DNS server's IP address, you can use that. If you do not know that, you can use this address. This IP address belongs to Google's public DNS server. Disable IPv6 configuration. To keep this tutorial simple, I will use only IPv4 addresses. The configuration steps for both IPv4 and IPv6 are the same. Access any website to verify the system can access the internet. Let's perform these steps in our virtual lab. I prepared this lab exclusively to explain RHCE exam topics. Since the RHCE exam does not allow candidates to use the internet, I did not configure this lab to use the internet. To perform the exercises explained in this video, we need to connect all virtual machines to the internet. To do this, we need to change the network connection type. Currently, the network connection type of all 3 systems is LAN. We need to change it to bridged. A bridged connection allows the virtual system to access the host's internet connection. To change the network connection type, power off the virtual machine, open its settings, and click the network adapter option. On the open window, select the network connection type to bridged. Repeat the same process on RHEL Server 2 to change the connection type to bridged. Verify the connection type has changed. Now change the RHEL client's connection type to bridged. Verify the updated connection type on all 3 systems. Now power on all virtual machines. Log in from the root account and update the IP configuration. To update and verify the IP configuration, we can use the named.UI utility. It works on both CLI and GUI interfaces and provides a curses-based interface to manage interfaces. Open a terminal. Run the named.UI command. Select the Edit a Connection option and press the Enter key. Open the Ethernet interfaces setting. Change the IPv4 configuration to manual. Assign the IP address 192.168.29.100. Configure the modem's IP address here. Configure Google's public DNS server's IP address here. Disable IPv6 configuration. Save the connection. To apply the changes, we need to restart the interface. Select the Activate a Connection option and press the Enter key. To restart the interface, first, deactivate it and then activate it again. Quit the utility. To verify internet access, we can use the ping command. If you get replies, it verifies the system can access Google's website. On the GUI interface, we can also use a browser. Open Firefox and access any website to verify the internet access. On RHEL Server 2, we need to repeat the same process again. Log in from the root account. Run the nmtui command. Select the Edit a Connection option and press the Enter key. Open the Ethernet interfaces setting. Change the IP4 configuration to manual. Assign the IP address 192.168.29.101. Configure the modem's IP address here. Configure Google's public DNS server's IP address here. Disable IP6 configuration. Save the connection. Restart the interface. For this, select the Activate a Connection option and press the Enter key. Select the connection and deactivate it. Activate it again. Quit the utility. To verify internet access, use the ping command. Repeat the same process on RHEL client. Log in from the root account. Run the nmtui command. Select the Edit a Connection option and press Enter key. Open the Ethernet interfaces setting. Change the IP4 configuration to manual. Assign the IP address 192.168.29.102. Configure the modem's IP address here. Configure Google's public DNS server's IP address here. Disable IP6 configuration. Save the connection. Select the Activate a Connection option and press the Enter key. Select the connection and deactivate it. Activate it again. Quit the utility. To verify internet access, use the ping command. We also need to test connectivity between all three systems. Let's send ping requests to RHEL Server 1 and RHEL Server 2 to test connectivity. As we can see here, all three systems are connected and have internet access. The named service runs the DNS server. The bind package provides the named service. The bind utils package provides the tools we need to manage the named service. We need to install both packages on the system which we want to use as a DNS server. In this lab, we will use RHEL Server 1 and RHEL Server 2 as DNS servers. Therefore, we need to install these packages on these systems. RHEL Linux installs packages from repositories. When we install RHEL Linux, the installation process automatically configures the system to use Red Hat's online repositories. To use these repositories, we need to purchase Red Hat's subscription. If you have Red Hat's active subscription and the system is connected to the internet, you can install packages from Red Hat's online repositories. If you don't have Red Hat's active subscription, you can configure a local repository from RHEL's installation disk and use it to install packages. To learn how to do this, you can check this video. Let's install both packages on both systems. To install packages, we use the dnf command. It supports many options and arguments for various functions. To install packages, it uses the install option. After the install option, we need to specify the package's name we want to install. If we want to install multiple packages, we can specify their names in a sequence. To separate package names, we use a single space between package names. To install the bind and bind utils packages, specify their names and press the Enter key. The command checks all specified packages on the system. If any package is already installed, it skips that package. It checks the dependencies of the remaining packages. If any package needs any additional packages, it automatically downloads them with the specified packages from the available repository. After downloading all packages, it calculates and prints the disk size they need, and asks the user to confirm the installation. To confirm the installation, we need to type the letter Y in lowercase and hit the Enter key. To cancel the installation, we need to type the letter N in uppercase and press the Enter key. Apart from the letters Y and N, all other letters are considered invalid input. For an invalid response, it prints the prompt again. To verify it, let's give an extra space after typing the letter Y and hit the Enter key. As we can see here, it is considered an invalid input. Type the letter Y again and press Enter key to confirm the installation. After confirmation, the command installs specified packages and prints the result. As we can see here, the package has been installed successfully. Repeat the same process on RHEL Server 2. Log in from the root account and installs the bind and bind utils package. Type the letter Y and press the Enter key to confirm the installation. As we can see here, the package has been installed successfully. Currently, the system is configured to use the ISP's default caching-only server or Google's public caching-only DNS server. Linux saves the caching-only DNS server's IP address in the /etc/resolve.conf file. To use a locally configured caching-only DNS server, we need to change this IP address. Start the nmtui utility. Open the connection. We will configure the caching-only name server on this system. Therefore, we will use this system's IP address here. Save the connection. To apply the change, we need to restart the connection. When we restart the connection, the Network Manager updates all configuration files to use the new configuration. Quit the utility. Verify the change. Named.conf is the main configuration file of the DNS server. When we install the bind package, the installation process copies this file from the package to the /etc directory. By default, this file is configured to run the DNS service as a caching-only DNS server on the local system. With the default configuration, it accepts queries only from the local system. To accept queries from other computers, we need to configure this option. It defines the IP addresses on which the DNS server will listen for queries. We need to add this computer's IP address here. This option defines client computers from which this server will accept queries. By default, it accepts queries only from the local system. To allow this server to accept queries from the local network, we need to add the local network's network ID here. Save the file. Restart the named service. If the service restarts without any error, the service is ready to resolve queries. If the service does not start or you get any error, check the named.conf file again. A small mistake in this file can block the service from starting. Let's understand it through the example. Open the file again. Remove this semicolon and save the file. Restart the service. As we can see here, the service does not start this time. If you don't know why a service fails to start, you should start debugging process from the systemctl command. Use this command with the status option. With the status option, this command prints the current state of the service. If a service failed to start, it prints the step or line number in which the service failed. As we can see here, the service failed on line number 11 because we missed a semicolon before the closing curly bracket. Open the file again. Add the semicolon and save the file. Restart the service. As we can see here, the service starts again without any error. DNS clients send DNS queries on port 53. There are two protocols, TCP and UDP. After verifying the DNS service is running, we need to verify that port 53 is open on both protocols. To verify it, we can use the netstat command. This command shows the open TCP ports. As we can see here, the DNS service is listening for DNS queries on port 53. To view the opened UDP port, change this option to U. As we can see here, port 53 is open on the UDP protocol. We have configured this system as the caching-only DNS server. To verify it, we can use the host command. This command sends a recursive query to the configured DNS server. As we can see here, the query has been resolved by the caching-only DNS server configured on the local system. To verify, the caching-only DNS server stores the result in the cache and uses it to resolve the subsequent queries for the same name. Let's send one more query. Since it received a recursive query for this name the first time, it resolved the query from the authoritative DNS servers and saved the result in the cache. It took 994 milliseconds to resolve this query. Now send the same query again. Since this time, it already has the answer to this query in the cache, it resolved the query from the cache. This time it took only 25 milliseconds to resolve the query. Let's send the same query again. This time it took only 22 milliseconds. It verifies the caching-only DNS server resolves queries from the cache. It uses the authoritative DNS servers to resolve a query only if the answer to the query is not available in the cache. DNS provides a command line tool called rndc for cache management. We can use this tool to view the cache data. DNS stores the cache data in an encrypted format. To view the cache data, first, we need to convert it into a regular text format. This command converts the cache data into regular text format and saves the output in the /var/name/data/cache_dump.db file. To find a particular record in the cache data, we can use the grep command. For example, this command finds all records related to the name google.com. The caching-only DNS server saves only the answers it receives from the authoritative name servers. It means you will find records only for the names that have been resolved by the caching-only DNS server. To verify it, let's find the name yahoo.com. Since we did not send any query for the name yahoo.com, there is no cache data for this name. Let's send a query for this name. Dump the cache data again and find the records related to this name. As we can see here, this time the cache has records for this name. It verifies the caching-only name server saves results in the cache and uses them for subsequent queries. Let's send one more query for the name yahoo.com and compare the time it takes to resolve. This time, it resolved the query from the cache and took 0 milliseconds. When it resolved the query from the authoritative DNS servers, it took 1 millisecond. It verifies a caching-only server increases DNS performance and reduces network loads by obtaining a single copy of frequently accessed information and making it available many times with no additional overhead. Now, let's test the caching-only DNS server from the DNS client computer. To configure a DNS client, we need to update its DNS server's IP address. Start the nmt.UI utility. Edit the connection to update its DNS server's IP address. We configured the caching-only DNS server on the RHEL server 1. Therefore, we will configure RHEL server 1's IP address here. Save the configuration. To apply the new configuration, we need to restart the connection. As mentioned earlier, Linux saves the DNS server's IP address in the /etc/resolve.conf file. We can check this file to confirm the DNS server's IP address has been updated. As we can see here, the system has been updated to use the local caching-only DNS server. Let's use the host command to send a DNS query to it. As we can see here, the client fails to reach the configured DNS server. Now, let's run the same command on RHEL server 1. As we can see here, RHEL server 1 can reach the configured DNS server. Can you guess why RHEL server 1 can reach and RHEL client cannot reach the configured DNS server while the configured DNS server is the same for both systems? The answer to this question is the default firewall. All RHEL Linux systems have a default firewall that does not allow other computers to access the services running on them. If you want to make a service publicly accessible, you have to configure the firewall to allow that service. The default firewall divides traffic into zones. By default, it enables the default zone. If you did not change the default zone, you need to DNS service in the allowed services of this zone. If you have changed or configured the other zone, you need to add the DNS server in that zone. This command prints the default zone's name. This command adds the DNS service in the allowed services of the default zone. It adds the service in the current session only. In the next session, you need to run this command again. If you want to add the DNS service permanently, use the permanent option. Now test from DNS client again. As we can see here, now the client can access the caching-only DNS server configured on RHEL server 1. Let's perform a few more tests. For each recursive query, the caching-only name server checks the cache. If the answer to the query is available in the cache, it provides the answer. If the answer to the query is not available in the cache, it communicates with the configured authoritative DNS servers, gets the answer, saves the answer in the cache, and provides the answer to the requester system. To verify it, we can check the cache data on the caching-only name server. Dump the cache data and search record for any query we sent from our HEL client. To delete the cache data, we use the flush option with the rndc command. Let's delete the cache data. To verify it, we can search for any previously resolved names. As we can see here, the cache data has been removed. A DNS forwarder is a resolver system that forwards all queries to the configured caching-only DNS server. Forwarding DNS queries to a caching-only server is called DNS forwarding. A DNS forwarder is similar to a caching-only name server. If we have a caching-only name server, we can easily convert it into a DNS forwarder. In our lab, we have configured and verified the caching-only name server on our HEL server 1. We will convert it into a DNS forwarder. Since a DNS forwarder forwards queries to a caching-only name server, we also need a caching-only name server. We will configure our HEL server 2 as the caching-only name server. To convert a caching-only name server into a DNS forwarder, we need to configure the two options, forwarders and forward only in the /etc/named.conf file. The forwarders option requires the IP address of the caching-only name server that will receive DNS queries from this system. In simple words, this system will forward DNS queries to the caching-only name servers configured in this option. In our lab, we will configure the caching-only DNS server on our HEL server 2. Our HEL server 2's IP address is 192.168.29.101. Therefore, we will add this IP address to this option. A DNS forwarder forwards DNS queries to the configured caching-only name server. If DNS queries fail because of a server error or timeout, a forwarder starts working as the caching-only name server. When it receives a recursive query, it forwards the query to the configured caching-only DNS server. If it receives the answer to the query, it saves the answer in the cache and provides the answer to the requester. If it does not receive the answer to the query or the configured caching-only DNS server is down, it directly communicates with the authoritative DNS servers and resolves the query. In simple words, if the configured caching-only server is up, it works as a DNS forwarder. If the configured caching-only DNS server is down, it works as a caching-only DNS server. This is the default behavior of a DNS forwarder. The forward-only option overrides this behavior and configures the name server as a DNS forwarder-only server. If we configure this option, the system works as a DNS forwarder only. If the configured caching-only DNS server is down, it does not resolve the query itself. But it can use its cache to answer the query. So if the answer to the query is already available in the cache, the client will get the answer to the query even if the configured caching-only DNS server is down. Let's understand it through an example. Suppose a client sends a query to resolve the name yahoo.com to a DNS forwarder-only system. The system checks its cache to find the DNS records related to the name yahoo.com. If it finds the records, it provides them to the requester system. If it does not find the records, it forwards the query to the configured caching-only DNS server. The caching-only DNS server resolves the query and replies to the DNS forwarder system. The forwarder system saves the answer in the cache and replies to the requester client. Now suppose, the configured caching-only DNS server is down and another client sends a query to resolve the name yahoo.com to the DNS forwarder-only system. Since the answer to the query is available in the cache, the system replies from the cache. It does not forward the query to the configured caching-only DNS server. This way, even if the caching-only DNS server is down, the DNS forwarder system can resolve queries from its cache. But it will resolve only queries whose answers are available in the cache. If a query's answer is not available in the cache, it will not resolve the query. For example, a client sends a query to resolve the name Amazon.com to a DNS forwarder-only system. If the answer to this query is not available in the DNS forwarder-only system's cache and the configured caching-only DNS server is down, the client will get an error message indicating the host is not reachable. Configure both options and save the file. Flush the cache data. Restart the name service. Now, this system has been configured as a DNS forwarder only. It will forward all queries to the configured caching-only DNS server. Let's configure our HEL server 2 as the caching-only DNS server for the DNS forwarder system. Open the /etc/name.conf file. Add this system's IP address in this option. Add DNS client's network ID in this option. Save the file. Currently, this system is configured to use Google's DNS server. Open the IP configuration and update the DNS server's IP address. We will configure the caching-only DNS server on this system. To configure this system to use the locally configured caching-only DNS server, we need to change this IP address. Save the configuration. Restart the connection to apply the change. Restart the named service. Verify the system is configured to use the locally configured caching-only DNS server. Send a recursive query to test the configured caching-only DNS server. As we can see here, the query has been resolved successfully. It verifies the caching-only DNS server is working properly. Verify port 53 is open on both protocols. Add a allow rule for the DNS service in the default zone of the firewall. If we don't add this rule, DNS client systems cannot access the caching-only DNS server configured on this system. If you want to add this rule permanently, you can use the permanent option. Before we test this server configuration from the DNS client system, let's verify the server is caching the records. For this, dump the cache data. Search records for any previously sent query. As we can see here, the server is properly caching the records. Now, let's flush the cache to perform new tests. To test and verify the DNS forwarder-only configuration, check the cache data on rhel server 1. Since we have already flushed the cache data, there must be no data in the cache. As we can see here, the cache is empty. Now send a recursive query from the client system to it. As we can see here, the query has been resolved successfully. Let's understand how this query was resolved. rhel client, which is configured as a DNS client system, sent this query to rhel server 1. rhel server 1 is configured as a DNS forwarder only. It checked its cache and found no answer to this query. Since the answer to the query was not available in the cache, it forwarded the query to the rhel server 2. rhel server 2 is configured as a caching-only DNS server. It resolved the query, cached the answer, and replied to the rhel server 1. rhel server 1 did the same thing. It cached the answer and replied to the rhel client. To verify it, let's check the cache data on rhel server 1 and rhel server 2. Remember, we flushed the cache data on both systems before performing this test. So, if we see any cache data on both systems, it must be generated because of the query we sent in this test. As we can see here, the answer to the query has been cached on the DNS forwarder-only system. Now let's check on the caching-only DNS server. As we can see here, the answer to the query has been cached on the caching-only DNS server as well. Now let's verify the fact that says, if the forwarder system resolves queries from the cache even if the caching-only DNS server is down. For this, ping yahoo.com. Since at this time, both the caching-only and forwarder systems are up, the yahoo.com will be translated from the caching-only server and the answer will be saved on both systems. Now stop the named service on the caching-only DNS server. Send ping request to msn.com. Since the answer to this name is not available in the forwarder system's cache and the caching-only DNS server is down, it must fail. Now ping google.com. The answer to this name is available in the forwarder system's cache. Therefore, it should be translated. Now send another request to amazon.com. It should fail. These tests verify the forwarder system uses its cache to answer the queries. Now start the named service on the caching-only DNS server and test again. As we can see here, the queries have been resolved. It verifies the setup in which the forwarder-only DNS server forwards and the caching-only DNS server resolves the queries. That's all for this video. If you have any suggestions, comments, or feedback about this video, please share them with us in the comment section given below.